Welcome to the Dork Forest. Jackie and her pals will never bore us. Shameless confessions
about our obsession
will make us laugh and smile. So let's explore the Dork Forest and dork out for a while.
Happy New Year! Hi, I'm Jackie Cation. You're listening to the Dork Forest. It is available on all of the websites, and including iTunes and Stitcher and YouTube. And if you go to dorkforest.com or jackiecation.com, you'll find links to all of it. And then I have another podcast with Lori Kilmartin just about stand-up comedy. But this is the Dork Forest, and it's January 2020, so Happy New Year, and feel free to start donating again. That's right. Donations went off last year, and I don't blame you, but think of me. And PayPal will let you do it monthly if you want, but I understand if you don't want, because monthly is its own commitment. But the people who do it monthly, I said do. I totally appreciate that. But there is also going to be new merch. I'm phasing out one of the Dork Forest t-shirts. I think it's the black one. It might be the green one. The green one's almost completely out of stock, so I think it might be the Dork Forest one itself, but feel free to try and order stuff so that I can get those two new shirts on the website, because right now the merch page is a bit crowded, shall we say. By the way, my website is done by Vilmos. You know that. The song that was just sang was composed by Mike Rickberg. He'll sing his version of the Mexican hat dance at the end of the program, and Patrick Brady is going to fix this audio and has been doing it for these many years, and I genuinely appreciate that about him so much. The new shirts are going to be a shirt with a bunch of my dad's sayings and a drawing of his face on that Jenny Fine did. And Jenny Fine, of course, was the artist who did the Meat Shield t-shirt, and she also did the art for the Horcrux album and DVD. You can get all of my old merch still at JackieCation.com, and the new merch, feel free to email me, Jackie@JackieCation.com, and we'll figure it out, is what I'm saying. I'm going to record a new album in 2020, but I don't know where or when. Feel free to come and watch me work on the new hour. At JackieCation.com has all of my tour dates, and at JackieCation on Twitter, Instagram, Snapchat. There's also a Dork Forest Ranger page that you can get into. Donations, PayPal, Venmo, do whatever you need to do. But I'm very appreciative of everybody's support over the last 13 years. Let's get into some dorkdoms, shall we? Hey, this is Jackie Cation. I'm in my living room, but because of the thing, my guest is not in her living room. And hello and welcome to the program, Luisa Rebull.
Hi.
Right?
Yeah, no, I'm in my basement. It's pretty boring.
Ooh, you have a basement?
Yes, well, it's a split level house, so I still have daylight, but the floor is concrete, so
Fair enough. Luisa Rebull, by the way, works CalTech at the Infrared Science at URSA, Infrared Science Archive.
Yep.
And we're going to be talking astronomy. You study the rotation and variability of young stars.
I do.
We did an episode that's on Facebook and it's archived. It was a live Facebook thing called Universe Unplugged. And we met and you were fascinating.
Oh, good. I'm glad.
And so I have this to say. Hooray. Welcome to the program.
Thank you.
So I like to start all of my science-based Dork Forest with this little anecdote. I have a friend who teaches AP physics. And one time we were playing a board game and I said to Judy Adler, we've conquered gravity, right? Like we could control gravity, right? And that's what she did. She laughed. And she said, what have you been reading? And so talk to me, because you're like an astrophysicist or you're a rocket scientist or some damn thing, right?
Yeah, no, it's a lot of fun. So yeah, I study how stars form and I study the rotation rates of stars. So most of the time, you don't think very much about the sun, but without the sun, we wouldn't be here. And without magnetic fields, the sun would be as boring boring as most people think it is. And because the sun has magnetic fields, it has all of these spots and flares and coronal mass ejections, basically big explosions on the surface of the sun. And those surface blemishes rotate into and out of view so that we can figure out how fast the sun rotates. And Galileo did this. That's part of why he went blind, unfortunately, was because he was studying the sun through his telescope, watching the spots move across the sun. And so the sun rotates in about a month at the equator. It goes around about 28 days, and goes slower at the poles because the equator goes faster. It's a fluid. It's a plasma. The sun is, so it's not solid at all. It's not like the Earth, where the Earth is a clump of rock and rotates as a solid body essentially. But the sun is very different. The sun is made out of plasma, and so the equator rotates faster than the poles. And stars that are younger than the sun have even stronger magnetic fields. And so whereas at its most active, we might have a few percent of the sun's face covered in spots, where for these young stars, you can have more than half the face of the star covered in spots. So as the star rotates, you see relatively large changes in brightness as the star rotates the spot goes into and out of view. And so you see a relatively large change in brightness. And so you can figure out how fast the star is spinning.
Wow. So, okay. Cause you're like, it's like when you do, I don't do ballet, but when you do ballet and when you spin, you're supposed to look at a spot, a stationary spot. So you're the stationary spot and you're watching that plasma ball spin.
Yeah.
And every time a flare you've seen before come up, you can sort of figure out how fast the rotation is because of that?
Yeah, well, the spot, really. So the spots produce the flares and sometimes the explosions, but the spots persist for a couple of rotations, and so you can watch them. They'll rotate out of view, and you wait long enough, and they do come back around. But yeah, you're absolutely right with the idea of a skater, of a ballet dancer spinning. You're right that she keeps her head still so she doesn't get motion sick, right? Skaters aren't so lucky. Skaters, that when they spin really, really fast, and when they start out, often their arms are out and maybe a leg is out, and as they pull in their arms and the leg, they go faster and faster and faster and faster and faster. Stars do that too. So the very earliest, very youngest stars are pretty big. They're big clouds of gas and dust, and as that gas and dust collapses, it starts spinning faster and faster and faster and faster. And for a long time, nobody understood how stars could even form, because if you just work on the math, they should basically spin themselves apart before they create a star. So trying to understand, because spin like that is one of those things in the universe that's conserved. Like you have to keep track of where the energy is, and you have to keep track of where the spin is, the angular momentum. And so when you have a big cloud spinning very slowly, it becomes a small star spinning very, very, very fast, and trying to figure out where all that spin went is part of what I'm doing, trying to figure out where the angular momentum is going. And some people think it might have something to do with planet formation. It certainly involves magnetic fields and all sorts of complicated fluid dynamics. It's really cool, but it's still a puzzle. Understanding the rotational evolution of stars is really confusing.
Right. Okay. So now you've mentioned it a couple of times. You have to know that my big takeaway from 8th grade science, which was I think the last science I've taken, was I can draw Snoopy. So not cool. So the magnetic force, is that different than gravity, or is that the same? What do we know?
It is different. So it's different. So you can, if you just stand in the middle of your kitchen and drop a magnet, it falls. But if you stand in the same kitchen and put the magnet on your fridge, it doesn't fall. Right?
Right.
So you've got, electricity and magnetism tend to operate on smaller scales than gravity usually does. Gravity usually is operating on large scales. But, certainly in your kitchen, you can make electricity and magnetism beat gravity, right? Because the magnet sticks on your fridge. So so magnets, magnetism is a really, really complicated thing. It's like, so for years when I was in grad school, they would always say, if you slept through colloquium and you're trying to look intelligent, you can raise your hand during the question period and say, have you considered magnetic fields? Because almost certainly nobody has. And it makes it sound like you were paying attention the whole time and really engaged with what the speaker was saying. Because almost certainly they ignored magnetic fields, and almost certainly they make a difference. So magnetic fields makes the astrophysics complicated, because you have to take into account, a whole bunch of effects that, it'd be easier to ignore.
Right. And what is colloquial? What is that?
Colloquium. Sorry, it's most departments have like a weekly formal talk. Nobody does at the moment because COVID-19. But yeah. So here in Pasadena, there are many talks on any given week. You could spend a significant, on a normal week. What's normal anymore? But on a normal week, you could spend a significant fraction of your week just going to talks because there are many institutions in Pasadena that do astronomy. There's CalTech, where I work, but then there's also the Carnegie Observatories, which is north of the 210, and there's JPL, which is
Jet Propulsion
the Jet
Labs,
Propulsion
right?
Lab up the hill, and there's you go a little bit further west and you hit UCLA, go a little bit further east and you hit Pomona. And so there's lots of astronomy going on, in the Los Angeles area. So you could just go to talks all week because there's usually some talk somewhere.
Right. And those are called
colloquia. Yeah. Sorry.
Thank you.
Like seminars. Seminars also, is also
seminars.
Yeah. It's just
right. And talks.
Yeah.
And
there's a lot of PowerPoint. There's
people made graphs.
Yes,
people
exactly.
made graphics.
Exactly.
And it can be about anything with astronomy. It covers all of. It's available in all of those different places. They could discuss anything, whether it's stars or planets or
pretty much. I mean, the different institutions have different strengths. So there are people like at JPL who study the immediate Earth environment because the Earth has a magnetic field, and that's a really good thing because the magnetic field helps protect us from the explosions on the sun, right? Because then when there's a big explosion on the sun, that exploding material moves out through the solar system, and it's all charged, which means that it sees the magnetic field. And the Earth's magnetic field basically pushes the stuff around and avoids, the stuff doesn't hit Earth. It gets channeled around the magnetic field. And so there are people who study the dynamics of the Earth's magnetic field. And so that's really close by. And there are people at JPL that study the moon. And then there are people in all of these institutions that study things in our solar system. There's lots of people at JPL that study things in our solar system. But then there are, people who study things at the very edge of our solar system, and people that study the other stars, and people that study other stars, far away in our galaxy, and the people that study other galaxies, and the people who study things at the edge of the universe. So the talks will go every week. There's talks from everything, right? There's talks from really local stuff to really far away stuff.
Exactly. And so stars are like our sun is a star.
Yes.
Let us start at the beginning. And our sun is a star, and it is not a young star. It's a medium star.
Yeah, it's kind of a middle-aged star.
That's nice.
Yeah, it's in the middle of its life, comfortably puttering along.
Excellent. And then and so what is then our planets obviously this is feel free to start a drinking game, everyone. So the planets go around the star.
Yes.
And that is the Milky Way?
No, nope.
Damn it.
Yeah, so when we were doing the Universe Unplugged thing, we were talking about stars form. So let's do a quick review for the people that didn't yet go look at the Universe Unplugged video.
Yeah.
So stars start as a big cloud of gas and dust, and they collapse down. And because of the way the physics works, it doesn't all just go whoop into a ball in the middle. It falls onto a disk first. So I used to be able to say things like a CD or a record, but who does those things anymore? So
I burned a CD yesterday for my dad.
Well, there you go. So maybe Frisbee would be a better analogy.
Right.
I'm not sure. But a disc, right? A disc of matter. Right. And then from that disc, the stuff continues to fall onto the young star at the center. But that disc, because everything in the disc is moving in the same direction in a plane, that is how you end up with the solar systems like we have, right? With all the planets going in the same direction around the sun in a plane, right? So that's how you get planetary systems that are all going the same direction, all pretty much in the same plane. Now, so
the disk is our the disk is our solar system.
Yeah, it's our baby solar system. Yeah.
Okay. And the bigger solar system is the. Go ahead.
No, so that's how you get the solar system, right? That's how you get all the planets in a plane moving in the same direction. And then when you get out of our solar system and you start to look at the other stars, then you find that there's a whole bunch of stars in our galaxy, the Milky Way, and those are also
a galaxy.
Yeah, it's our galaxy. So the Milky Way also, just like a young star system, has a big mass at the center and then a disk of stuff around it. It's just in the case of a young star, you've got a baby star in the center and a disk of stuff around it that's going to become planets. But in the case of the Milky Way, you've got a supermassive black hole in the center and then a disk of other stars, all going around it in the same direction, pretty much. So
what?
Yeah, it's the same physics, just a much different scale. But yeah.
Wait, in the center of the Milky Way, there's a black hole?
Yeah, a supermassive black hole. It's pretty cool. Yeah.
It sounds amazing.
It is amazing.
I don't know why I didn't know.
It is amazing.
Why didn't I?
So there's a group at UCLA that specializes in this. And you can go, if you Google UCLA Center of the Galaxy, you'll find some amazing videos. So what they do is they track how the stars near the center of the galaxy move over years, human years, right? And you end up with watching these stars whip around the center of the galaxy, from which, if you do the math, you can figure out that, there's a big black hole in the center of our galaxy. And it's really cool. So if you Google the UCLA Center of the Galaxy, you'll eventually find some really cool movies that show the movement of the stars. It's really neat.
Right. I believe that this makes math much more interesting than it's ever been before.
Well, of course. It's always much more fun to do actual science with it because, grinding log division just makes everybody miserable. It's much more interesting to do actual science.
Yeah, like I don't want to decline all of the verbs in Latin. I want to talk Latin.
Exactly.
Anyway.
Yes,
so
exactly.
That's awesome. Okay, so there's a solar system, there's a galaxy, and then is there something bigger before we just get to the whole rest of the universe?
So our nearest little galaxy neighbors are the Large Magellanic and the Small Magellanic Clouds. And those of us here in the Northern Hemisphere don't really see those things, but the people who live in the Southern Hemisphere are very familiar with them because you can see them from the Southern Hemisphere, and they're sort of big, blotchy things in the sky, and those are our nearest galaxy neighbors. And for years, it was thought that they were on a collision course with the Milky Way, but I learned at a conference recently that they actually probably have already gone through the Milky Way at least once. So they're coming back around for another hit.
Are they lapping us?
Yeah. And then our nearest big galaxy neighbor is the Andromeda Galaxy, M31. And that we are going to hit eventually. We will no longer be here by then, but the two galaxies will collide. And then outside of M31 and Andromeda, there's a bunch of galaxies called the local group. And so that's our clump of galaxies. And then you get out from there into the web of galaxies and the rest of the universe.
That sounds hipstery, the local group. It sounds like it's been gentrified somehow.
Astronomers are not that good at coming up with names. I mean, come on, the Big Bang. I really like Calvin's suggestion of the horrendous space kablooey. But, we have things called the Very Large Telescope. I mean, honestly, people, we can come up with a better name.
Okay, who came up with the Big Bang? Who named it?
So it was originally a derogatory term when people were trying to figure out how the universe was formed. Somebody did the math and said, well, it looks like there was a really big explosion. And people were like, oh, you've got to be kidding me. And so it started out as sort of a derogatory term. It's like, Big Bang. And then that's what got adopted as the term for it. So, and then after that Calvin and Hobbes cartoon from the 80s where they called it the horrendous space kablooey for a few years, people actually were putting horrendous space kablooey in the journal articles. So if you look, you can find references to the HSK for the horrendous space kablooey.
Space kablooey. Yeah, I wish they would have called it that.
It would be so much more fun.
It would be. Did you ever read? Now, I digress, but allow me to ask, have you ever read The Dragon Riders of Pern by Anne McCaffrey?
Yes, I did.
And there's a prequel where they describe the settling of that planet, and so the not the settling, but the discovery of that planet. Essentially, the research group that landed on it to find out if it was habitable. Guess what they missed? Thread. Anyway, because they were only there for a month because they had a couple of problems.
Right.
But they named it PERN, which stood for Parallel Earth Resources Negligible.
Oh, that's great. Yes, I know. I'm not sure I ever read the prequel. I've read a bunch of those books, but it has been a long time since I have read those books.
Well, they're super fun.
They are. I loved them.
Yeah, and the prequel is just a novella, I think. I think it's called... well, I've lost it. Anyway, but people can look it up, and but because it is kind of, it's about essentially the people. The first of it's an anthology. So the first novella is them discovering the planet and finding it habitable, flying away, and then the first settlers coming and trying to essentially and discovering Thread.
Right.
And what a pain in the ass that was.
Yes.
And then, but they find the fire lizards.
Oh,
and then
yes.
They make them into dragons. So that's kind of cool.
It is
who
cool.
doesn't want the tale of the making of dragons?
Yes, especially telepathic dragons. Those were awesome.
Exactly. You link with at birth. Who doesn't want that?
Exactly.
Your best friend?
Exactly.
Right. I am on board. So come here. There we go. My computer went dark, and I was like, "Don't lose it."
Oh no.
Okay. Here's my next question. So I want to know about what got you into astronomy.
So
I almost said astrology.
Oh
I
yeah,
am
that
so
would have been
sorry.
bad. Yeah. No, I have always been interested in astronomy. I never remember a time in which I wasn't interested in astronomy. I was the only little girl in kindergarten, apparently, who did not bring a doll to share at the post-Christmas, show and tell. I brought my motorized Legos because I had not put them down since I got them. I came home in tears, wondering why my mom hadn't given me a doll. And my mom said, "You did get a doll. It's still in the packaging over there."
What were the motorized Legos?
Oh, they were really cool. Now Legos have gotten even more sophisticated than they were then, but it was just basically a simple motor, and you could, you could basically put in the gears to make, like a Ferris wheel or something actually turn. Yeah. Right. So that was a new thing when I was a kid, and I thought that was just awesome. So,
so you were an engineering baby.
Yeah. And
You're
science,
like, I want to be an engineering and science. You're like, yeah, we're gonna look into how things work.
Yeah, exactly. But I did fall off the wagon for a while because this was the 70s. And, my parents did the best they could trying to encourage me. But I absorbed from the culture that girls weren't supposed to be able to do math. And so I fell off the wagon for a while in late elementary school and middle school because, girls can't do math.
Did you get pretty? Did you get super pretty?
No.
Did you get into it?
No, I didn't. And that, it was like an identity crisis for middle school.
Me neither. Me neither.
But certainly in the beginning of high school, I was like, yeah, I'm going to figure this out, and by college,
screw these people.
Exactly. Yeah. And by college, I was like, I'm actually doing okay here. This is good. So, yeah.
Right. So in high school, you probably took all of the sciences and all of the maths because you were like, screw this. I'm just going to take the classes that I want to take.
Yeah. I was the only girl in the 7th grade science class. Yep.
Oh, wow. Yeah. Because I know two of my older siblings, because I have 6 older siblings.
Oh, my goodness.
or 5 older siblings. And the first 3, we have 2 separate, essentially, ways that we grew up. My 3 older brothers were raised to take shop. And then my 4th oldest brother was like, I'm not taking shop, I'm taking trig, and I'm taking chemistry, and I'm taking this.
Yep.
And then my sisters, just slightly older than me, said, I am also taking trig and chemistry, and I am going to college.
Excellent.
And so when it got to me, I wanted to take art and shop.
Yep.
But I was in the group of people that were taking trig and chemistry. And so I passed chemistry, not well, but it was, but I never ended up taking physics or any of the higher math, the higher maths beyond trig. And
Well, it's hard to take those in high school because they're trying to cram so much information into you that there's not a lot of, actually playing with data and actually doing something that looks like real science, because science as it's taught at the high school, at most high school and most college levels, tends to be here, have a problem set and work through the problem set, right? Or read the textbook and do the problem set. But real science is nothing like that, right? Because textbook science has a series of questions, and that each one of the questions has an answer, and that 3 could be right and 4 could be wrong, and that there's a specific set of steps you're supposed to do to get the answer, right? But real science is totally different because there's no cookbook, there's no set of steps you're supposed to follow. You're wandering around on the edge of human knowledge, and so you have to figure out what your question is and how you're going to go about answering it. And this is not something that can be done, during a lab class, right? It's not a 3-hour thing. It could be months or even years. And working along, and you think you're doing the right thing, and then it becomes apparent that, oh no, you made a big mistake 3 months ago, and you got to go back and redo it all. So and you could
like knitting.
Yes,
like if you drop a stitch,
exactly.
you have to go, oh my God, I have to undo 17 rows to get back to that one stitch.
Exactly.
That is fascinating.
Yeah. So so real science is really, really different than the science you get exposed to, in most high school classes, or even a lot of the college classes.
Well, I suppose it takes, they want to teach you the basics, and they want to make sure that it's sort of like art, where you're like, you have to know how to draw a hand.
Right.
To draw a hand, you have to know how to do perspective, and you have to know how to make things. So there's all of these sort of grinding it out. Again, Latin, the memorization of verbs is annoying.
You have to get fluent in the language and the math, right, before you can do the more advanced stuff. But
Right. And you work in education right now, right?
Yeah. One of my jobs is to run a program called NITARP, which is the NASA IPAC Teacher Archive Research Program. And so what I do is I partner small groups of mostly high school educators with a research astronomer for a year-long real research experience. And so we do the real thing. It's not a matter of, here's a set of questions, don't look at the back of the book for the answers. We are doing real science. We are trying to figure out.
We're hoping that you will discover something.
Right, exactly.
That'd be awesome.
Exactly. And so
you and your fresh elastic brain.
So trying to help the teachers get a sense of what real science is like and how different it is than textbook science. And they get to bring along students too, so the students learn as well. But the reason we work with teachers is because of the multiplicative factor, right? Because if I work with a student, that's great. If I change that student's life, that's great. That's awesome. Yeah. Don't get me wrong. But if I change the teacher's life, then I am changing the way that he or she teaches science to the 30 kids they have in each of 6 periods this year, next year, the year after, and the year after.
Ongoing.
And so that multiplicative effect is why we work with teachers, because honestly, there's not that many professional astronomers in the U.S. And so we have to rely on deputies, right? We have to use that kind of multiplication factor, because I can't go out and teach everybody. So I have to, I teach teachers so that they can go out and teach everybody.
Right. It's, that I like to bring it down to the mundane after you've said something profound. Allow me to tell, I once got my hair cut at a fancy hairdresser salon in London, England. And it was one of those schools, right? You could go for $15 or 20 pounds or whatever it was. And these were men and women hairdressers from around the United States and the world who had come to this fancy Aveda salon to learn from amazing hairdressers.
Right.
And so the instructor was wandering around, helping people, pointing out, what they were doing right, what they were doing wrong. He comes to my chair and he goes, "This is great. This is, you're building it right. You're doing this. The layers are wonderful." The next time he comes around, he goes, "You've ruined it."
Oh, no.
And so I looked in the mirror. I was like, "What happened?" And I of course couldn't tell, because I was just getting a haircut. But but it was like that, where you're like, everyone has all this amazing, there's someone who's amazing at what they do, and to sort of create apprentices or apostles or the multiplicative is a great word, and I will be practicing it in front of the mirror.
Well, another analogy that I like to use is, because I grew up in the Washington, D.C. area where football is king. And I don't care how poor your school is in Virginia or for that matter, Texas, you are going to have a football coach who's actually played football. You would never ask somebody to be the football coach if they had never played football. And there's a huge amount of jargon you need to learn in order to play football properly, in order to explain what the plays are. You have to understand the perspective that they're coming from and what they're asking you to do. But in science, very few high school teachers have ever done real science. Few of them have even worked with real data. And so we're asking them to teach science without ever having done it. And that's a big ask. And a lot of the teachers are working really hard to do that. But that is hard, especially given the new standards that are coming through where they're being asked to teach science in a more authentic way. If they've never done it, gosh, that's a big, big hill to climb. Yeah. And so that's why we're doing what we're doing, is to try to help them understand, oh, this is how science works. Okay. And
that is so cool.
Yeah, I think so anyway.
Yeah. Do you have, we can get back to education, but I was going to ask you if you had any sort of, because you were talking about Galileo, like who were your sort of inspirational? I'm sure this is like people asking me who my favorite comics are, but do you have good scientist stories for me? Oh, that's what I'm hoping for.
Sure. So, I try to take advantage of all of the good examples of behavior and techniques and people that I see around me. So I try to learn from everyone all the time. And there is so I was at the IAU, the International Astronomical Union meeting in Prague, the Czech Republic. And that meeting, so the IAU is the big organization of professional astronomers worldwide. And they have meetings every few years, and they are in charge of naming things. And so they had decided a couple of IAUs prior to demote Pluto. And it went over very poorly with the community at large. And so they assembled another committee, this time consisting of historians and astronomers. And I think there was even a sociologist on the committee. Oh, wow. And they were going to make formal recommendations, again, revising their previous opinion. They were going to make formal recommendations about Pluto. And so they had a special lunch meeting at the IAU. And they spent, in my opinion, unfortunately, a good chunk of their dedicated hour being rather self-congratulatory on all the work that they had done. And then they announced that they were going to demote Pluto again.
Oh, my God.
They're human. Yeah. So there was very little time for discussion. And the few people that did get up, most of the time people at astronomy meetings are very, very polite. They're very formal, but at this meeting there was actual yelling. Okay. In the comment period afterwards, somebody yelled, I do such and such. And if it was good enough for Kepler, it ought to be good enough for you. It was really amazing. And so
that's a great line.
Exactly. So that particular part of the meeting did not go well. And there was grassroots rebellion all over the meeting. And so they had to have additional splinter meetings during the whole rest of the week, a week and a half, whatever it was, to try to come to agreement on what was going on. And so what's really going on is it's just a matter of what you call things, right? So let me digress for a little bit. So if you define a sandwich, right? So it's got to be, if you define a sandwich as meat between two pieces of bread, well, you've left out a vegetarian sandwich, and you've also left out like an open-faced sandwich, right? Oh, right. And so now you have to expand your definition to include open-faced sandwiches, but then a pizza is bread with meat on it. So does that make a pizza a sandwich? And then what about hot dogs? Where do hot dogs fit in? Are hot dog sandwiches? Right?
Or a meat pie.
Exactly. So it gets really complicated quickly, but in part that's an artificial restriction depending on how you want to define sandwich, right? So here, that's the same thing with the planets in our solar system, right? So when I mentioned earlier that when our planets formed, they were all in the disk, of the proto-solar system, and they all ended up being formed out of the disk, so they're all in the plane going the same direction. Pluto is an oddball. Pluto is not in the plane. Pluto is actually quite inclined. And so we've known it was weird.
Wait, say that again. Quite what?
It's not. It's very different, right? It's inclined. It's at an angle.
Okay.
So it's not. Okay. It's not quite in the plane of the galaxy. I mean, sorry, plane of the solar system. Right. So it's at a. It's clearly different, right? It's a clearly different than the other planets, right? And also in our solar system, we've got a whole bunch of rocky things close to the sun, and then a whole bunch of gassy things further out, and then Pluto is once again rocky. So Pluto is just weird in a lot of ways. Yeah. And, as our understanding of the contents of our solar system have evolved, we've learned that there are lots of other things like Pluto out there. They're in a thing called that's called the Kuiper Belt, and those guys are also remnants of our disk, our original formation disk, but they are very far out, and some of them are bigger than Pluto. And they're all kind of like that. They're not quite, they're sort of in the plane, but not quite in the plane. And they're rocky ice balls. And it turns out that, there are things larger than Pluto. So if you want to call Pluto a planet, then you probably should also call the things out in, its brethren out there also planets. Right. Right. And then you start to say, okay, well, if Pluto is big enough to be a planet, what about Ceres? Ceres is the largest thing in the asteroid belt. Right? So should that be a planet?
Is that also a planet?
Yeah, it just gets very complicated. And so the decision, it's just a matter of what you call it, right? And so we're going to call Ceres and Pluto and its friends out there in the Kuiper Belt dwarf planets, meaning that they're not a planet like Jupiter, they're not a planet like Earth or Mars, but they are still planets. They're just dwarf planets. It's just a different adjective. But at any rate, going back to the IOU, in the context of this, there was legions of angry astronomers and people who were publishing screeds and distributing them on paper during the meeting, and wholesale rebellion. So it's just a little terrifying, right? So there's
especially if you're used to a certain decorum, you're like, what the, it's a free-for-all.
Yes. So Jocelyn Bell is a famous astronomer, and the reason she's famous is because she discovered pulsars, and her advisor got the Nobel Prize for it. So yeah, exactly. So she's famous for that, but she is also an amazing woman. She is very small in stature. She is a very tiny woman, but she dominated one of these discussions because she was on the IOU, like the board, basically.
The panel?
Yeah. Not the panel that reviewed the status of Pluto, but on the board that convened that panel, right? And so she ran one of these lunch meetings. And so she was standing in a room full of like 150 angry astronomers. And so here is this tiny woman bringing this entire herd of unruly astronomers to heel. She said, okay, I study pulsars. I have no personal stake in the status of whether or not Pluto's a planet, much less exoplanets. I study pulsars. I have no stake in this. So here's how it's going to go. You will have the mic for 45 seconds. If you cannot make your point in 45 seconds, I will cut you off. And so she did. She had a series of comments, and then she put up on, at the time we had an overhead projector, I think, because I think she was writing out longhand. So she said, okay, well, what about these words? And then she would stop everybody, put up the words, let people have a chance to read the words, and then she would take a vote. Is this okay? Is this not okay? And then based on the response, she would change a word or change a sentence. And okay, will this be okay? Yes, okay, let's go. So she took this group of 150, 200 angry astronomers, brought them to heel, and made discernible progress on this very contentious matter in the space of an hour. She was amazing. She's
a freaking hero.
Exactly. So things like that are the kinds of things that I try to remember, right? The next time I have to be trying to bring a group of angry cats to herd.
Right. And literally, I mean, her having no horse in that race had to simplify it. I mean, were the other groups sometimes run by people who did have a horse in that race?
So she was trying to make the group go forward and change it from what was just a complaining session or a ranting session into something that was actually making forward progress. But the people that were most angry about this were people who studied things in our solar system. You know, is this a planet? Is it not a planet? And are the other things that are being found out there planets or not? But then the other people that were angry were people who studied exoplanets, because if you're going to call a certain number of things in our solar system planets, then you have to think about what the ramifications are for that naming scheme when you start finding other planets. And so the definition that came out of that meeting sounds a little strange and dorky, and among other things, the term clear its orbit or something to that effect, which indicates that asteroids that are surrounded by debris, right, wouldn't be counted as planets. But an asteroid that has enough mass to pull itself into a sphere, which Ceres does, that means it's a dwarf planet. So Pluto has enough mass that it too can pull itself by its own self-gravity into a sphere. So that is also a planet.
And here we go back to basics when I ask this question. Saturn has rings. That looks like debris for me.
It does.
Is that not debris?
It is debris, but the gaps in the it's big enough. Yeah. Maybe. So the gaps. So the physics, right, of the thin disk around the planet is the same kind of physics we've been talking about before, because this is the same sort of physics where you have a central young star and a disk of matter going around it, or the Milky Way with the mass in the center and the disk going around it. So it's the same physics. It's just different scale. And you're absolutely right that the rings of Saturn are very, very thin compared to the rest of Saturn. And the gaps in those disks or the gaps in that ring, rather, are created by moonlets. Right, the disks, the ring itself was probably formed from a disrupted moon that was literally pulled apart by Saturn's gravity. The gaps in the rings are because you have these little moonlets, or these moons. They're sometimes called shepherd moons because they're shepherding the matter in the ring around. And so it's those gaps that when you have a gap, you can probably figure out that there's a little moon or moonlet creating it.
Right,
and that same.
Do you remember? Oh, go ahead.
No, I was just going to say that same physics works elsewhere too, right? We're looking at, disks around other stars, and they have gaps. And so do they have planets? That's exactly what some people are trying to figure out right now, is does a gap mean there has to be a planet, or can there be a gap if there's just another planet making another gap nearby? That's all I was going to say. Sorry, go ahead.
Yeah. Oh, no, my question was I forget how many moons Jupiter has.
Oh, both Jupiter and Saturn have a ton. Oh, my gosh. I don't even remember. Yeah.
Right, but piles.
Tens and tens of them, yeah. And I think Neptune just got 30 more, I think. I can't remember.
Oh, they found 30 more?
Yeah, no, because there's these little tiny rocks, right? And these big gas giants snag these little tiny rocks, from comets as they're coming by, or, leftover debris from the solar system formation. So, yeah, there's a lot of little moons. Yeah, there's legions of them.
And this isn't, you probably know this, but what is the moon made of?
Rock.
Rock. Just a pile of rock.
Yeah, pretty much.
It's not minerals. It's not. Is it? No. What kind of rock? Is it granite? Is it limestone? What are we looking at?
That's a good question. So I am not a geologist, but my understanding is that limestone you need water. And I don't think the moon has had very much water. So our best understanding of how the moon formed was in the young solar system. There was a proto-Earth, and there was another object in our orbit that was about the size of Mars. And so as the planets were forming, it was kind of a rough and tumble environment, and it hit us, right? And so that impact pulled off some debris from Earth. And so the Earth-Moon system probably had a ring at some point, a ring of debris that before it got collected up. And when the moon was formed, it was very close to us, but we're steadily losing the moon. So it's further now than it was when the dinosaurs were here. So the moon is literally made up of the same thing that the Earth is, the inner Earth is. So, so the same kinds of volcanic rock is what most of the moon is. There is some water there, not a lot. There's no atmosphere on the moon. So, obviously it's a much different place than Earth, but the core of it is similar to the core, to the deep inside the Earth, because it was made from the same stuff.
Oh, right. Yeah. I was going to say that one of my favorite science classes, because I had to take certain science classes in college to get the science, there were required classes, right?
Right.
And I took one class, which I thought was going to be easy. It was called The History of the Weather.
Oh, that sounds like fun.
Right. I thought it was going to be it was a lot of graphs. It was not what I was looking for. What it was a lot of science, not a lot of history.
Right.
And but I took this other class, which was literally just the history of science, is what it was called, and that was what I was looking for. They would explain Galileo's principles, and then they would tell us the gossip about Galileo.
Oh, there you go.
And that was my favorite. That was one of my favorite science classes in college. So I can't remember who the original astronomers were. I mean, in Western society, it was the Greeks, right?
Yeah, but also the Arabs, right? There's lots of Arabian astronomers. Right. That's how you end up with names that are, names of stars that are mangled Arabic, right? It's because of that heritage. Yeah.
And nobody knows how to pronounce it, so they're just saying
it's been mangled beyond belief. Like Betelgeuse, we're not even sure what Arabic that might have come from. There's two different camps, one of which thinks it's the shoulder of the giant, and the other camp thinks it's I think it was the goat with the black spot on it, or something strange like that.
Right, because they all come from
Arabic words, yeah.
Right, from Arabic words and from Arabic mythology, much like much of the Greek mythology.
Yep.
Because I remember when it was the Dark Ages in Europe, it was a Renaissance in Northern Africa and the Arab world, if I remember correctly.
And then when the Europeans had the Renaissance, they picked up the education from the Arabic books, right?
Right. Yeah. It was a discovery of all of the things they had been working on for 100 years, 200 years. That's kind of fascinating. And then I had another question. What else? So let's go back. I mean, we're doing good, but we have some time. What are your favorite things that you're studying right now that are kind of cool?
Gosh, bear with me because we're going to have to go a little bit deep here. So trying to understand, we started out talking a little bit about the sun's rotation, right? And so there's a lot of missions and a lot of surveys going on right now trying to find exoplanets, right? And a lot of them are looking for exoplanet transit. So what that means is you've got the star and the planet, way far away, but the planet orbiting the star makes a teeny tiny little dip. And in order to believe that the planet is there, you have to see at least one, preferably more, of these transits, right? Where the planet is moving in between us and the star, creating a tiny little dip. Well, the spots on the stars are enormous, and so they create much bigger dips. And so a lot of the people studying exoplanets are specifically avoiding the stars with big spots because that just makes it a whole lot harder to find the planets.
Right.
But I, of course, am interested in the stars. I mean, planets are cool and all, but I'm interested in the stars, right? And so I sort of get the leavings of a lot of these exoplanet missions because I care about the stars, right? And so and
there's still plenty of data of that.
so much data. So there was a mission called Kepler, which flew a while ago, and its original mission, which it completed, was to stare at one chunk of sky for literally years, looking for these tiny little dips due to the exoplanets. And they deliberately picked this field to consist of lots of older stars, so they wouldn't have to worry about the star variability to find the planets. And and then so in order to steer a spacecraft, you have gyroscopes on the spacecraft, and you need at least 3 in order to point a spacecraft and to keep it pointing in the same position. Because if you're looking for really tiny dips, you've got to keep that telescope pointed in exactly the same place, no wobbling, in order for you to find the little tiny dips that are exoplanets. Well, Kepler had a bunch of gyros on board, and they broke, and it was down to just 2 gyros, and they still had enough fuel on board, and the spacecraft was still working just fine. It's just that it had only 2 gyros. So lots and lots of clever engineers got together and figured out how we can make this work. So basically, they used the 2 gyros they had left, and then for the third dimension of control, they used, believe it or not, the pressure from the solar wind. So I'm doing this right now, and of course you can't see me. So the spacecraft would point in 2 directions just fine, and then be blown by the solar wind over, and it would use a little fuel to push back, and then blown over and push back. So sort of like a rocking chair. It would move like this, right?
Like a pendulum.
Yeah, kind of. And so the spacecraft was still working, and the data were still phenomenal because you're capable of looking for little tiny changes, but now you're limited with where you can point. And as a result of this, we had then access to stars of a much larger range of masses and ages than we ever thought was going to be possible with this. And so the people who were looking for planets, and so these campaigns would go for about 70 days, and they'd pick another field and do 70 days and then do another field. So I have I have a whole new appreciation for mailman, right? Because the mail just keeps coming. You can never get on top of it. And the data from this mission just kept coming and coming and coming.
Oh, wow.
And you cannot process it fast enough to get the science out. So I am swimming in data from this mission. The mission finally ended. It ran out of fuel, but I have no shortage of data. I just submitted a paper that involved data, I think, from campaign 4 and 12, and I think there were 18 campaigns. So I have a lot of data still to go through. So that's what I've been spending a lot of time on lately, is looking at how the rotation rate changes in all of these stars of different masses and different ages than we ever thought we'd be able to see, and trying to understand, which ones are going fast and which ones are going slow. And I have a whole bunch that go around in hours, and, they're spinning so fast that it's likely that they're close to breakup. In other words, they're close to spinning themselves apart. And then I have lots of others that are going mysteriously very, very, very slowly, like longer than 30 days. So, yeah, it's really cool. It's a puzzle, but it's really cool.
That's a cool puzzle. I have this very basic question. I've heard of it. I'm sure someone has explained it to me. Can you explain it to me again? What is a gyroscope?
So it's a cool toy, right? If you've ever had one, I think
it's a cool toy. I've seen it.
Yeah. And they have basically 3 nested rings that rotate in different directions. And so the one that I had as a kid was metal, and you could put a string around, wrap it around the top, and then you'd pull off the string really fast and get it spinning, and then it would be amazingly stable, right? It would balance on one end of so there was an axis that went through the whole thing, a metal axis, and it would balance on one end of that for a really long time until the wheels slowed down due to friction, and then it would fall over. So
it's like a top.
Yeah, kind of. Only it's got a top is usually solid, and the gyroscope is going to have rings able to go in 3 different directions. So the magic of it is that, remember earlier I was talking about you have to keep track of where the spin is going, right? Okay. When you get this thing going, you've got all sorts of angular momentum, and so that's that conservation of angular momentum, that keeping that spin energy, so to speak, is what's keeping it stable. And when you're in space, if you build your gyros right, you don't have a lot of friction. And so they just always spin. And the way that you control the spacecraft is you change the spin in one direction of some of the gyros. And then the spacecraft moves in response because spin.
Oh my God, that's so cool.
It is really cool. Really complicated, but really cool.
Yeah. That I appreciate you putting that in an English that I'm like, oh, I get that. It'll be gone in about 2 hours.
Well, but the key point is that it helps it stabilize, right? It's using spinning to help stabilize, which is sort of counterintuitive, but it works.
Yeah. The other thing was I was going to... Where was that question? Oh, here it is. It was, so there is one of those universeunplugged.org, by the way. People could go there if they want to see the half hour that we did together with another scientist, and we talked about stars. But I've done a couple other episodes with them, and one of them was about exoplanets. Yep. And I learned what an exoplanet was, which was amazing. And there was an Australian astrophysicist.
Jesse.
That's it. And she tweeted a thing the other day. It was a picture of Elon Musk's Occupy Mars logo. And she said, for the last time, that's the moon.
Yeah.
So you're like, there are pictures of Mars, right?
Yes,
like he could have
many pictures of Mars. Yes.
So he could have put a picture of Mars on the logo.
Yeah, you'd
but
think.
People recognize the moon. Maybe it's a marketing strategy.
I don't know.
That is, who knows what he's doing, and but that is fascinating. So what? How do you spell Kepler?
Kepler. So just
one P.
yeah. And he was Kepler the man was a Polish astronomer, and he figured out how the planets move in our solar system. And so when they were building a mission to look for other planets, they thought Kepler would be an appropriate name. So Kepler is the name of the mission as well. And when the mission changed to use just two of the gyros, it became called K2, meaning like the second generation, but also K2 like the summit, like climbing a high mountain, something difficult to accomplish, right? So it's the name of that portion of the mission, even though it was the same physical spacecraft, is K2. Because
they didn't know how it would work.
Exactly.
It was quite a thing.
Yeah, exactly.
And now, so the Kepler, that the whole thing's over. You have more data than you can shake a stick at.
Oh yeah.
And what are the current? Are there current like stars? Like, are there spaceships looking at star systems right now, or is it mostly telescope work?
Well, you mean are there? I'm not sure what you're asking, because the all of NASA's missions, right? When you think of robot, you think of like what's his face, the danger Will Robinson, right? You think of, or C-3PO, right, or R2D2.
Sure.
But all of these uncrewed missions, right, whether it's a spacecraft of any sort, right, something that looks at the Earth or something that looks at the Moon or something that goes to Mars, they're all robots, right? They're all they're all built to operate somewhat at least autonomously, right? Because they're empowered to do something and then call home and check in and get more instructions and then go off and do the next thing. So all of them are robots in that sense. The robots that drive around Mars are, of course, completely different than the ones that, like Kepler, that orbit the sun and, send back data every so often. So they're all space robots. But there are a lot of both ground-based and space-based missions that are looking for planets. There's a mission called TESS right now, which is observing lots and lots of relatively nearby bright stars to try to look for those little teeny tiny dips that signify that there's a planet there, or more than one.
But are there spacecraft out? Like, is Kepler still sending data?
No, but it's still in orbit. Just like Spitzer is no longer sending data, but also still in orbit. So both Kepler and Spitzer have similar orbits. They're trailing behind the Earth. They're orbiting the sun. They're not orbiting the Earth. They're orbiting the sun. So they're trailing behind the Earth.
Oh yeah, and for years have been sending data of what they're seeing when they look at the sun.
It's a common misconception that I've encountered more than once that spacecraft like Hubble fly out to these places and then come back. No, Hubble's in orbit around the Earth, and so it's just a matter of pointing the spacecraft and staring for a long time at these fabulous places, because they're all so far away. We can never ever go visit them. So we're just taking advantage of all the light that we can, and by that I mean not just the optical light, but light that we can't see with our own eyes, like infrared or X-rays. We try to take advantage of all the different kinds of light coming from these things, because they're, we can't, not only can we not ever go visit them, we can't pick them up and turn them around or put them in a jar in a lab and watch them. These are all things we can't, it makes us different from a lot of science, because we can't go visit these places. And so we're just trying to figure out as much as we can from what we have. And it's interesting because there are sort of overlaps with other fields, like the medical imaging field and astronomy imaging have, taken advantage of each other's advancements in terms of image processing. But the medical imaging, of course, you can turn the person around, right? You can take a picture of the injury from another direction. Which you can never do in astronomy.
Right.
So, so it's very different. So we're just trying to take advantage of all of the light that we have from these objects to try to figure out what they are.
And so we send them into space because the magnetism and or the gravity or whatever, there's a lot of sort of static on the Earth. If we can get it out into space, it clears it up.
It's the main thing is the atmosphere, right? I love the atmosphere. It keeps us warm and keeps us breathing. This is a really good thing. Yeah. But the atmosphere is not very stable and it absorbs a lot of the light or scatters it depending on the wavelength. So there's in order to take really, really precise images, in terms by which I mean like really high spatial resolution, like really fine, I'm trying to think of a good analogy, because focus implies another whole Pandora's box of things. But if you want to take pictures of things that are really close together, you have to get up above the atmosphere so that the atmosphere doesn't smear it out, so that you can actually see the two distinct objects that you know are there. And so that's the main thing, is to get up above the atmosphere, because if you're an ultraviolet astronomer, the UV doesn't really make it down to the ground. I mean, I know that's hard to believe after you spent the day at the ballpark or whatever and you're burned to a crisp, but that's the UV from the sun, which is really, really strong. And it scatters, right? Because if you go to the beach, then the UV light bounces off the water and the sand and gets you burned even faster. That UV light from celestial sources doesn't make it unscathed through the atmosphere. So if you're an ultraviolet astronomer, you got to go to space. And for a lot of infrared too, you have to go to space. For X-rays, you have to go to space, just because you have to get up above the atmosphere. And so that's the main reason people go to space, is to get up above the atmosphere, either because the light doesn't make it all the way through, or because the light blurs out it smears the objects.
Wow. Holy smokes. Well, what you should know, by the way, I have mentioned your name once. Luisa Rebull, right?
Yes.
Am I putting the accent on the right? Rebull?
Yes.
There we go. It is L Rebull on Twitter, probably Instagram too, and all the things?
Yes, I think so. I'm not very active on Instagram, but yes.
Okay, yeah. And you work over at CalTech, and you work at NASA, and it's or with NASA, and science.
Yes, lots of science.
So lots and lots of science. This has been a fascinating. I have learned things that are very basic that I should have remembered, and I've also I love to be reminded, and I love to be the person that asks that question, because maybe somebody did not know.
Absolutely, absolutely. And there's no dumb questions. I mean, the only dumb thing is to not ask them, because I'm sitting here, chatting with you. You might as well ask them. I mean, come on.
I might as well. Right, and you have been incredibly generous with your time with your brain box.
My pleasure.
So I appreciate that so much. So thank you so much for doing the show.
No problem. My pleasure.
And Rangers, you know the rules out there, and it's more important than ever. Take care of each other.
And wash your hands.
My hat, my hat, my hat. They're dancing around my hat. My hat, my hat, my hat. Well, what do you think of that? If it looks like a Mexican hat dance and it sounds like a Mexican hat dance, it's most likely a Mexican hat dance. So take off your hat and let's dance.
Yay! Oh my God. Why don't we just call that as the end of the show?